Yeah, thank you for the introduction, Rick. Yeah, as you take a look out of the window of our lecture theater, you will see a lot of trees, and there's like a reason because people generally like trees. And my talk is about why, in statistics, trees-based methods can be a good way or like a beneficial way to a number of questions, basically. So generally, I think tree methods have like three advantages over a set of different methods, which I will go into. So tree methods are basically, they're a form of like machine learning algorithm or statistical learning algorithms. And the main idea of this talk is based like on a paper from my PhD, but it's also really well explained in a book called Elements of Statistical Learning. And so the advantage of the tree method is basically that it is a form of a machine learning algorithm that is at the same time like very interpretable. So it can be used, for example, when you want to make very transparent, for example, why a specific outcome is performed, or why someone, for example, performs a specific action. At the same time, you don't really have to do a lot of assumptions about the behavior that you want to explain. And nonetheless, it is quite accurate. For example, if you would compare it to other more sophisticated things like neural networks or something, which I will go into detail now. So briefly, I will compare like 4 different tree-based methods, basically going from the most simple approach, I would say, like a pruned tree, which is basically, I will show a diagram of a normal tree diagram later, but which is basically just like this kind of decision tree most of you might be familiar with, and this is like a very interpretable version of it. Then you can kind of tune it up a bit more, and then you can aggregate multiple bootstraps of the same tree. Bootstrapping for those who are not familiar with it is basically the idea. If you have a sample, let's say you have a sample of 100 participants, and you just draw like a random sample out of that, like 1,000 times or something, and we will see how that also works with trees. And then you have like the third algorithm I will go into, which is like a random forest, which is probably like the most known like in different fields, because it is quite good. I mean, it is quite accurate, basically. But we will see that it's not always necessary to perform like the most sophisticated options. And fourth is a different form of a tree, which is called extreme gradient boosting, which is basically in the random forest. It's called random forest because it's like random feature. That's why it's called RF usually, because the features are selected randomly, and then in the XGB you basically weigh different forests differently according to their prediction error. I will explain this on an example from my research. So basically, you can take any behavior that you want to predict, or any outcome measures. And the example I will do is we will predict the sharing of like a drunk content on social media. So basically, adolescents who post on social media like a kind of a content where they're drunk themselves. And so the question is, why would they do that? So for that purpose, we did a data collection like among 1,600 Belgian adolescents. And before I will go in the code for that, don't get confused by the machine learning lingo. So it will be talking about target vector, which is basically nothing else than a dependent variable, and features, which is like kind of an independent variable, or endogenous, exogenous. So we'll basically start with the basic tree. So to kind of go into that, what you would kind of need to do, you create a training and a test data set. That's what you would always do in machine learning applications, because otherwise you would tend to overfit your model. So you would basically kind of do it in 2 parts. We just made a 50-50 split, and then you basically include some control parameters for your tree. So, for example, like what the minimum cut size is. We'll see later specifically what cuts are, what the minimum size means, and then you can just estimate the tree. We estimate the tree here by a function that's called rpart, that basically is short for the method of recursive partitioning. And you can think of recursive partitioning as like as some kind of dendrogram. So you have like a sample or like a specific set, and then you kind of divide that set like among the branches of the tree. That's also why you have these kind of splits. Don't consider the labels at the moment too much, but at the very top, for example, you have like that's called like the root of the tree, and then you can basically separate your sample among the split value. That's like here we have a variable that is like the exposure to drunk references on social media. So if you see them, you can basically then split the sample in two groups, and then you have like more of these cuts. And what you see on the end of these trees are leaves, which are basically the values of the variable that you investigate. Usually you would kind of, for example, standardize it in percentages or use like a standardized value to make it interpretable. In this example, it is just the raw value of our of the variable that we want to explain. But as you see in this tree here, it's kind of messy. It's not very easy to interpret. So what you would do, you would kind of prune the tree, and pruning means like cutting off unnecessary branches. So what you would do for that, you could, for example, compute your R square in relation to the number of splits that you have, and then you see, for example, after like 5 splits, like the increase gets relatively low. It's a bit like the elbow method, what you have like with PCA or something. So, and then you would kind of re-estimate your tree, and then just specify like the number of here the number of cuts, or the number of splits, or the number of here we specify the number of leaves that we have. So we say, okay, we want to have 6 leaves, and then you have like 6 different endpoints. And I think the biggest advantage of that method already becomes clear in that figure, because you can take like any given behavior, for example, here we have like exposure to drunk, we have like the sharing of drunk references, which is not that severe, but you could also basically extend it to any behavior, any epidemiological things that you're interested. So why would someone get vaccinated, or why would someone perform a specific behavior, and you can kind of nicely give the results according to these cuts. So, and then we can kind of see whether the thing that we did, whether it's accurate. So, for example, what you can do, like it's kind of similar to how you would, for example, test the outcomes of a logistic regression. You just use your model to make some predictions on your test data set based on from the training data set, and then you could, for example, usually what it gives you is like the mean square error, and so what you could do is you could calculate from the mean square error, you could put it in relation to your standard deviation, and then you could see that with the pruned tree model, we receive basically here a value of like 91. So that means, it's a bit smaller than the standard deviation. So if it would be 1, it would be just as good as taking the mean. So 1 would be like, there's no point in making the model. As you see here, we have like 99. It's not, 90.9. It's not really, it doesn't seem so strong yet. So, and we want to make it a bit stronger. We want to have more accurate predictions to publish like a nice paper and explain behavior. So what we could do now, we could now try the bagging method, which uses bootstrapping, which is basically you draw a number of random samples from your sample, and on most you basically run the trees. And then you can see, like with the number of trees, we run like 100 trees, it gets the mean square error in the training data set gets smaller and smaller. So we basically did that, and now we want to see whether that increased our predictions. So you can see it had an effect. So there's a point of making of bootstrapping that, but it also yeah, it's not yet a game changer, I would say. So what we can do, we can go more fancy. So we can now do like a random forest. So the difference of the random forest and the bootstrap aggregation is that in the random forest we also use a subset of the features. So remember, like features, these are like our variables, and there you can see all the variables. We have like a list of variables. You can just basically throw anything in because they will select themselves. It's machine learning. And you basically, all these trees draw like also a random set of variables. So you bootstrap and a random set of variables. And by doing so, that is the nice thing about the random forest. You can also kind of see which variables are most important across all of these trees. So what you see there is, for example, it is one on the left side, it's the scale is like the increase in mean square error if you would drop one of these variables. And then you can see, for example, like the exposure to these references is like the most strong predictor. And if you would drop that, your mean square error would increase drastically, and that would kind of drive down your model's performance. Whereas, for example, the bottom, the fear of negative evaluation is not important at all, which kind of makes sense. If you don't care what people think of you on the internet, yeah, then it's then you post these kind of references. So again, we can test this by making predictions again, and we see it hasn't really changed so much, the random forest. So although it's way more computationally heavy and a bit more difficult to interpret, it is not really, it doesn't defeat, you know, the standard pruning approach by a lot. But we can go more fancy. So we can do extreme gradient boosting, which is kind of a recent add to these techniques. The original CART algorithm, like the classification and regression tree algorithm, was from the 80s, and this is like from 2019 or like this is newer stuff. So there are two packages. At least I found two packages to do that. There's like the include XG boosting package and the H2O library. To be fair, we tried it with our team with the XG boost package. For some reason, it didn't work well. So if someone tries it, doesn't get good results, you're not the only one. But on the H2O platform, it kind of had a positive, it kind of went better. So there we needed a slightly different connotation, basically. But what we do is the same thing. We split our data frame. We define features and responses. And then we basically train it and predict it again. And here we see like a major improvement. So here we have like our predictions are only 0.6 of the standard deviation. And that really makes a difference over the mean model. So we can basically kind of show that by these variables, if we use these variables, we can actually explain the behavior, which might not come through in the initial models. The reason why this is so much better, or why the result is better, is because if you have a prediction of your random forest, basically, and you have like we have like for a specific set of your bootstrap sum, for a specific set, you have like a very bad prediction. The gradient boosting will say, oh, that's a bad prediction. Maybe we should pay more attention to that and see why that prediction is so much off. And then we weigh this prediction differently, and that leads to this drastic improvement, basically, of results. So when it comes to conclusions, I think there is one straight conclusion is that the XGB is far superior. Like also, at least in our example, I don't have oversight over where there's like a comprehensive literature comparison in different fields. But at least in our example, the XGB was kind of very different performance also than the random forest. The second thing worth showing here is also think that the basic prune tree, which is like which is a very kind of basic method. It is not so much worse than the random forest. So you could also kind of make the point that for specific research questions, I would say it is maybe not so it's maybe not so important to get this 5% of extra accuracy, but to rather stick with something that is more interpretable. Because it seems like this wouldn't give you so much edge. Or what you could also do, what we did in this paper, is you can just compare them and then say, oh, we can also stick with the most interpretable version, because if we go fancy, we don't gain a lot of accuracy. That's basically it. Thanks.